Hey, welcome back. Continuing on through chapter 4 here, we're sort of talking about species distributions and some of the underlying factors that influence how a species and how and where a species is distributed. I want to talk about some of the ecological foundations here and sort of um, the basics of ecology and some population dynamic stuff. And so a species range, and the reason why I want to talk about this is because the species range depends on the dynamics that control population growth and population decline or population change in general. So if we were to introduce this idea, and if you've ever taken a ecology course, you've probably ran into some of these models where a rate of population growth is a function of how a population is increasing and how a population is decreasing. And specifically, there's some different ways that that can happen. So, population, the most obvious way is new organisms can be born, through reproduction, or they can immigrate from a different population. We're not talking about an entire species. We're just talking about a population or a subset of a species. And so, new individuals could immigrate to from some population to this population, whatever population we're looking at. So either one of those ways would cause the population to increase. On the flip side of that coin are ways in which a population can decrease. One of those is obvious is individuals experiencing mortality or dying. Another way would be individuals leaving. So, they can show up or they can leave. And so the total rate of change is going to depend on a function of these things, new individuals being born, new individuals showing up, individuals deceased or dying, or leaving. And so those together are going to be the population change, and it may not always be growth. I should probably not say growth. It could be rate of population change, because if this is greater than this, then it's not going to be growth. It's going to be population decline. But if resources are, sort of this is kind of simplistic, and it's more for conceptual understanding than reflecting any reality, because this would be this you can get runaway growth with this model, and if resources, there were no limitations for resources, then you'd have infinite sort of population growth, which isn't really something that happens in the real world, except except if you're looking at humans for over historically. And you can get exponential growth in things like bacteria and other species too for periods of time, but not forever. And humans aren't going to be doing this forever either. In fact, most models are showing probably a leveling off. I think sometime this century, human population is probably going to level off and then start to decline a little bit. And we're not going to get into too much of that right now, but I just want to talk about, you can get this exponential unlimited growth, but it typically does not happen. And there's reasons why it doesn't happen, and there's more advanced models. I don't really want to get into population ecology too much, because that's not necessarily what this course is, but it's worth understanding some of those ideas. And if you're looking at an environment, looking at a species over the conditions in which it exists, there's usually some environmental gradient. So I don't know, we're talking about your favorite species here, whatever that is. And this is, maybe this is temperature gradient here. So you have low temperature and high temperature. There's some range, there's some range of temperature that organism, that species is well adapted to, and that might be referred to as the range of optimum. And it's going to be different for every species, because different species are adapted to different things, but there's some range, and that's where you're going to see the greatest abundance. And this is, the organisms are not stressed here for this particular environmental factor or variable, and so they're reproducing here and they're not dying as often here, and so you get really high abundance. And this is all relative, this is sort of theoretical and hypothetical, because it's going to be different for every species. But as you move away from that, you're sort of getting into areas where there's more physiological stress, and so maybe individuals die more often, or maybe they don't reproduce as often, or they don't show up to this location and stay for as often, and so the population levels are lower as you move away from this range, this optimal range. They can tolerate it here, they can exist here, but that uh, the population levels are lower. But if you go to the extremes in a relative sense for whatever you happen to be looking at, then you get to an area where they just can't tolerate that, just can't survive at all, and so you get this sort of shape that this is sort of a range of conditions, that a range of this environment, the conditions for this environmental factor that could influence that. And we can ultimately say environmental conditions limit the abundance and distribution of a species. And if that sort of sounds familiar to you, it's because we're basically describing this thing called niche theory or niche theory. I don't care how you say it. You can say it either way. If you've taken an ecology course, you've probably been introduced to this. The whole idea is essentially what we just described, that environmental conditions are going to control where a species is found. And the environmental niche is sort of the conditions under which an organism has adapted to and is well suited to. And we could be talking about anything. So here we're sort of breaking this down a little bit more simply. So we're looking at temperature here, and again, there's some range of temperature for whatever this species is. It doesn't matter. There's some range for temperature where the population will grow because that's what it's well adapted to, and there's some range of temperature. If you push beyond that, then you get to an area where the population will actually decline. This is a negative population growth would be a population decline. Because the individuals of the species are stressed, and so they don't survive or they don't reproduce or whatever the case may be. The population declines outside of this range, and you could do the same thing for another variable. You just add a variable and say, okay, let's look at salinity, and maybe this is an aquatic species, so we're looking at water salinity, and it's the same sort of thing. You have some range. Now the range looks like, we don't have units on this, but the range looks like it's narrower here, and so you still have this range of optimum water salinity, where here's where the species can tolerate it and tolerates it well and can exist and reproduce, and outside of that it doesn't, and the population actually shrinks. And what we can do ultimately is combine these two things and say, okay, so here's the theoretical range of both salinity and temperature for where this species could exist, or the range of conditions under which this species could exist. And you can start to build an idea of sort of the multi-dimensional space. Is one way of saying it, a weird way of saying it, but like, we can visualize it with two variables. We can say, okay, even if you had units on here and actually had data, instead of just this theoretical stuff that we're talking about, you could do this. But once you start getting past two, it becomes kind of hard to visualize. But it's not hard to, I don't think, imagine the idea that, yeah, there's water salinity and there's water temperature, but there's also water depth and water pressure and water acidity and water movement. There's lots of other types of variables that would also influence the population levels, and all of those are going to have a range under which a given species can exist. And so if you combined all of them, you'd have this multi-dimensional space that's kind of hard to visualize, but you can kind of think about it conceptually. That if you could measure all of the potential variables that exist and quantify them, that would be that species niche, its ecological niche. So that's sort of what the ecological niche is. Now it brings us to an area of sort of the difference between where a species is located and where a species could be, and this is sort of the difference between the realized niche and the fundamental niche, where the realized niche is the conditions in which a species is found, and I should have colored these different. The fundamental niche is the full range of conditions in which a species could survive. So, and I kind of want to make a distinction here because I kind of refer to these things casually, but ecologists sometimes get upset. The niche space is sort of the theoretical multi-dimensional space that doesn't really exist. It's like just the set of conditions, that theoretical conditions where a species could survive. The niche is not an actual physical location. It's just the range of conditions. So the fundamental and realized niche are not necessarily physical locations or actual places. They're more conceptual, depending on the factors that influence these things. And it's a little abstract, but and I don't think it's a super important distinction. But some ecologists get upset when you start referring to the niche as an actual place. But the point here is that the realized niche are the conditions where you actually find the species. The fundamental niche is the full range where the species could exist, but it doesn't for some reason. Maybe if this is like a tree species and we have soil moisture on our y-axis and temperature on our x-axis here. Maybe there's a location with high levels of moisture and moderate levels of temperature that this given species could exist here, but maybe this actual location in the real world is really isolated or something, and this species just can't get there. If it did, it could survive there, but it can't physically get there since something is blocking it. So it could. So that whole thing is the fundamental niche. This is the realized niche. And where does this all come from? This is sort of the classical Joseph Connell, I think was his name, who did this famous study and came up with the foundations of niche theory. It existed before him, but this was sort of one of the first that really clearly stated what's an ecological niche. And what they did was they went to these rocky shores that had these intertidal zones where you had low tides and high tides that would move in and out. And there were these barnacle species that were distributed, and they had kind of specific distributions where on the upper slopes you had this Thamylus, I never remember how to say that, Thamylus stellatus species, and then you had this Balanus underneath it, and then you had this intermediate species that was sort of dispersed. And they wanted to know, why is this one up here and why is this one down here? So they just systematically removed these. They removed the Balanus from these, and what happened was that the Thamylus expanded down the shore. So the whole thing was Thamylus if you remove the Balanus. And then they did the opposite. They removed the Thamylus instead. But what happened here was that the Balanus did not necessarily move up. And what they were able to conclude is that the upper range here is limiting, basically the Thamylus upper range is limited by desiccation. Like it gets too dry up here for it to survive. But the competition between these two species is sort of keeping them in their respective spots. They can't compete as well down here, and Balanus can't compete as well up here. Now, it's worth noting that Thamylus did, you see this arrow here, sort of the fundamental niche. If Balanus didn't exist at all, if they just removed it like they did to test it, then the Thamylus would expand. So the fundamental range for a Thamylus is the whole shore here, the whole thing. Balanus didn't extend up, which for a number of reasons, but it didn't expand up. So its fundamental range was basically where it is. Its realized niche and fundamental niche are essentially the same. But this sort of was the first example to very clearly show, here's how the ecological niche could work in real life, and there are basically three niche variables. The desiccation, the predation, which I think I forgot to mention, by this species, which is a predator of both of them, and then the competition between these two for food and space. So those three variables alone are enough to explain the distribution of Thamylus stellatus on these rocky shores. And that was sort of a really simplified, in most environments, there's probably more than 3 variables that are going to explain something. This is sort of a unique situation and why it was perfect for this type of study. And sort of going back to that point that I was making about, if we're talking about the fundamental niche and the realized niche not being actual places, then the geographic range is sort of an extension or a reflection of the ecological niche. It's sort of the spatial reflection of the ecological niche. And in fact, if you wanted to superimpose those ideas, you could refer to something as the realized geographic range or the fundamental geographic range, and that would be the exact same concepts as the fundamental or realized ecological niche, where the realized geographic range is the actual places where you find a species, and the fundamental geographic range is the total the total geographic range that a species could occupy, but for some reason otherwise does not. There are a few complications with niche theory. It sounds, when you introduce the idea, you're like, oh, that makes perfect sense, and people sort of assume that this is a thing that exists. There's some debate about how useful the niche concept really is. It does work well in a lot of situations. Others it doesn't. And one of those complications is that there are for any species, there are locations that are inhabited by that species, but they are unfavorable. And this is if you take an ecology, you've probably been introduced to source sink dynamics, where here you have a population that is, let's say this is favorable, a favorable location. Here, births are exceeding deaths, so reproduction is happening, and it's happening faster than individuals are dying. So the population is growing here, and species are immigrating to this location. And this location, we'll consider this to be unfavorable. Here, the births are less than the deaths, so the conditions are not favorable, and organisms die more often than they are born, for whatever reason. So this would be the source population, this would be the sink population. If you didn't necessarily know that, if you just saw that, okay, this organism exists here and it exists here, this must be the full geographic range, the full realized range, and the conditions would represent the full niche. But you might not know that it can't actually survive here. The only reason this species is located here is because it immigrates from here to here. And so those source sink dynamics kind of complicate, is this part of the niche or is it not, is sort of a complicating factor there. Another one is just the fact that you have this unfilled niche space. So why if the conditions are possible for this organism to exist under these ranges, why doesn't it exist there? And it could be for a number of reasons. It could be that it doesn't, it can exist there, but it doesn't as well, and so maybe it saps the energy from that organism and it can't compete as well, or whatever it is. Maybe its reproduction doesn't work as well, or whatever it is. You have unfilled niche space, and that's sort of a complicating thing. Why would that exist at all, if these conditions are at least tolerable? And the last one is sort of the last complication is sort of a temporal one, whereas if you zoom out and start to look at these source sink population or dynamics over time, and I kind of just want to focus on metapopulations here, these dynamics change. So sometimes species will be located there, but then it'll go locally extinct. And then it's here, and then maybe later it goes locally extinct, and maybe it was here in the past and it's not anymore, or it wasn't in the past but it is now. You get this shifting sort of mosaic over time where species are moving around and maybe going extinct in one place and not in another. So which is the whole thing part of the niche, or is it not, can be a complicating factor as well. And so a few complications with that, and some things that not necessarily invalidate niche theory, but just shows how complex some of these things and interactions really are. Okay, so I think there's a reading here that probably does a better job than what I can do. So keep working your way through this, do the next reading, and I will see you, excuse me, I will see you in the next video.